it's an amazing welcome here to get applause before I've even said anything, and it's really been like that all week. I arrived, we got off the plane, practically everyone in Tel Aviv was on the streets waving flags to welcome me. So the first thing that happened when I came to write these slides was I realized I couldn't actually fit the title on the title slide. So if you look in the program, you'll notice that the title talks about compartmentalization and memory safety. And if in like a minute's time you all fall asleep and remember nothing else of this talk, I really want to get across that these are not two separate problems. If you build strong non-bypassable memory safety, you get compartmentalization basically for free. If you try and build compartmentalization without memory safety, you end up with something that just doesn't have a programmer model that anyone understands. And if you look at the most aggressively compartmentalized applications in the world, they've got like 7 compartments. And if you want to really compartmentalize, really deploy the principle of least privilege everywhere, you should be able to ship things with hundreds of compartments, thousands of compartments. And that means you need a programmer model that someone writing code who's not a security expert can look at and go, yeah, I kind of understand what that software is doing. So I'm going to talk about a bunch of stuff. None of this is secret Microsoft proprietary. Everything that we're doing in this project is open source, from the ISA, which we're contributing to RISC-V International, that we want to get standardized as a RISC-V extension, through the reference implementation of that on top of the Ibex core from lowRISC, to the clean slate compartmentalized RTOS, which I'm going to be talking about a lot today, and the compiler. So the entire hardware-software stack here is open source. If you want to grab the RTL for the core or build your own RISC-V core implementing these, fab a load of chips and ship devices built on it, please do. So this is kind of where we are. We've all seen this before, right? I can't stop people connecting light bulbs or thermostats or aluminum smelting plants or X-ray machines to the internet. I've tried, seriously. It just doesn't work. So what we really wanted to try and do with this project was see if we could design a chip that was about as cheap to build as ones with absolutely no security. So, same sort of area cost as M-profile ARM core or baseline RISC-V without even the basic, multiple privilege rings or the kinds of things you take for granted on larger systems. And in that same sort of cost, build something that gave us really game-changing security. And everyone pokes fun at IoT, but it's a really cost-driven ecosystem. If you're 6 months late to market or you're $1 more than your competitors, then that translates to no sales. There's very little regulatory pressure. There's very little consumer pressure to be secure. There's a lot of consumer pressure to get to market quickly. So our hope was that by co-designing our instruction set architecture, the implementation of that, the compartmentalization model, and the operating system that ties it all together, we'd be able to build something that could really change the absolute lowest baseline security guarantees for the cheapest possible devices, internet-enabled light bulbs, that kind of thing. So if you look at the IoT ecosystem, it's kind of a mess, right? There are loads of chunks of legacy code, usually in C, occasionally, if you're lucky, in C++, although often it's like 20-year-old C++, so you're actually not that lucky. These things were often written with the assumption that no one would ever connect this device to a network. So your adversary model is someone connecting physical probes to some pins and trying to break the device. It's not in any way assuming a software attacker. It comes from all over the place. It's in unsafe languages. It's not deployed with mitigations. And so, what we'd like to do in a lot of places is just say, well, we've got safe languages now. Let's just rewrite the code. And that's great, but now you need to find people who are expert Rust programmers, and that's kind of hard. You need to find people who are experts as embedded systems development, and that's actually really hard. And you need to find people who are experts in network security, and that's also pretty hard. So now you need to find people who are at the intersection of 3 areas with skills shortages. And did I mention that this is a cost-driven ecosystem? So yeah, you also need to not pay them any money. It actually gets worse than that, because a bunch of the things that we're often seeing people do on these embedded devices are intrinsically unsafe, right? There's code that is just below the level of an abstract machine for a safe language that's doing memory allocation, or more often it's talking directly to hardware devices. And the kind of properties that you need to be able to express just aren't there in any safe language. And if you can write things in safe languages, please do. So in fact, our reference implementation has a JavaScript interpreter, which is adopted from the Microbiome project, which is just a phenomenal piece of work. And so we can take JavaScript code, we can run it compartmentalized on one of these devices. And if you can get away with writing your embedded software in a type-safe, garbage-collected language, awesome, just do that. But for the bits that really need to be low-level code, we want to be able to get some very strong properties. So I could very easily stand here for 2-3 hours and send everyone in the audience to sleep talking about CHERI. I promise not to do that. So if you want a really good deep dive into CHERI, Sarah Ma gave a talk at Black Hat a couple of years ago. It's online. It's fantastic. Go and watch it. But for anyone who doesn't want me to pause for a while you all go and grab the phones and look at YouTube, I just want to give a sort of very brief overview. So CHERI is a project that started funded by DARPA in 2010. So this is not really exciting and new anymore. I started working on it in 2012. So, it's been around. The really key thing about CHERI is it teaches the hardware that pointers and integers are not the same thing. You have a type that the hardware understands that not just identifies a region of memory, but conveys access to that. So this contains bounds information, it contains permissions, and the hardware understands the set of operations that are allowed on this. So if I give you a pointer to an object, you can derive a pointer to a single field and pass that on, but you can't derive a pointer to the slab that the allocator carved that out from. And the really key thing is this is not advisory. This is not something that involves lookup tables. So it really takes the principle of intentionality down to the hardware level. Every memory access takes one of these hardware-defined pointer types as the operand that identifies the base address. So if you do a load or a store or a jump, you have to provide a hardware-defined pointer, and you have to have the rights through that specific pointer to access that object. So if you go out of bounds in an array, for example, just because you happen to have the rights to the object that was allocated immediately after that doesn't mean that, hooray, your out of bounds access will work. There's one other feature of CHERI that I want to briefly mention that we build on quite a lot, which is this notion of sealing, where you have a single instruction that takes 2 of these pointer-like values. One of them really is a pointer. The other is sort of like a pointer, but in a different identifier space. And the thing you get out of this is a sealed pointer. So this is sort of like a pointer to an opaque type, but that opacity is enforced in hardware. If I use that as the base for a load or a store instruction, I'll get a trap saying, sorry, this is a sealed pointer, you can't do anything with it. The only thing that I can do with it, other than delete it, overwrite it with data, is pass it as one of the inputs to an unseal operation. And that unseal operation will fail unless I also pass it the thing that was used to seal it in the first place. If I give you some other data and you try and unseal it, then you get an untagged value, so a thing that we know in hardware is not a valid pointer, and if you try and use that for anything, it'll trap, and you can easily test it and say, is this a valid pointer? So this is sort of where we were at the start of the project. And I said CHERI's been around for a while, but most of the work has been on 64-bit systems. And actually, how many of you are following the conference Twitter feed? A few people? So if you've seen the video that we just put up there of the CherIoT system sitting on my desk, if you squint a little bit and look in the corner of that, you'll see there's an ARM Morello system, which is one of the 64-bit Neoverse N1 derived systems that ARM's produced. These are absolutely fantastic machines, and I'm kind of sad I only have one at work and not one at home. But to go from these large systems designed to run Unix or Windows operating systems and to scale it really down to tiny embedded devices, we had a lot of work to do. When you start with a CHERI system, you have your normal address in a pointer. So if you've got a 64-bit system, you've got a 64-bit address field, and you double that. So you've got 64 bits available for metadata, and that lets you encode the base and the permissions and all the other nice stuff. When you shrink it to 32 bits, you also halve the metadata size. And some of those things scale reasonably well. So the bounds encoding, it's not quite ideal because there's a lot of redundancy between the base of an object, the top of an object, and the address within that object that a pointer refers to, which allows us to fit effectively 3 64-bit values in less than 128 bits. And some of that redundancy is reduced when you try and shrink things down. But the number of permissions and everything else just doesn't intrinsically change. So we needed to find a way of taking twice as much information as we could fit and squeezing it into that tiny space. So one of the things that we did with the big CHERI systems is guarantee that out-of-bounds accesses are representable for at least 4K, because it turns out people who write C code for big Unix systems do terrible, terrible things with pointers. And as long as you bring them back into bounds before you dereference them, it's fine. Embedded code, it turns out people are a lot more careful. They have to target weird architectures like PIC24 and Harvard architectures and things with split memory layouts. And so they actually tend to follow the rules of C or the intersection of the rules of 12 different weird C dialects a lot more carefully. So we were able to get good bounds precision, but by not guaranteeing an out-of-bounds region. On the Morello system, I think we have 18 bits for the type that we use for the sealing mechanism from the last slide. We shrunk that down to 3 bits and added a software mechanism to virtualize that. And we also took a really hard look at the permissions to identify which ones just never make sense together. So one of the things that I wanted to do on the larger CHERI systems was say it's just impossible by construction to implement a pointer that allows both execute, so you can jump to it, and write access. So if you want to write a JIT, you need to have a writable pointer and an executable pointer. And then mmap came along, and it made me sad. But again, on embedded systems, we don't have legacy APIs that were designed for PDP-11s and slightly updated for VAXs to deal with. We have other exciting legacy APIs that give us different constraints. And of course, the first thing that you do when you're told, OK, you need to squeeze this thing into half as much space as you started with is go, right, what can we add? So we've added a few things that I think are really useful in the embedded space. One is a pair of transitive permissions. Actually, one of these we managed to get added to Morello. These don't just apply to a pointer, they apply to any pointer that you load at any level of indirection through that pointer. So we can use one of these to express deep immutability, and that means with a single bit flip in a register, I can take a pointer to some object, pass it to you, and at no level of indirection following pointers that you load through that object can you end up with something that's writable. So I can get really strong guarantees that if I pass a pointer to some complex object graph from one compartment to another, it's not going to modify it at all. And I can do the same thing with the no capture guarantee. So the global permission in our system is effectively the one that allows you to store that pointer anywhere other than the stack. And if I remove that, and I remove your ability to load pointers that have that, then you can store that pointer on the stack, but when you return, I know you haven't captured a copy of that pointer anywhere. We've also added support for temporal safety, and I'll talk about that in a second. So the temporal safety support, you can think of as being kind of similar to a 1-bit MTE scheme. We have 1 bit of shadow memory for every 8-byte granule of real normal addressable memory. Every time you load a pointer, the hardware will look up, will calculate the base address of that pointer. So remember, pointers in a CHERI system have a base and a top and an address somewhere in the middle. We know that the base is always within the range that the allocator handed out because we have that monotonicity property. So you can reduce the range, but you can't ever increase it. If that base is within the range that's designated as usable by the heap, then the hardware will do an additional read to the shadow space, look up that bit in the bitmap, and if it's set to a 1, it invalidates the pointer. So this is a really simple degenerate example of a use after free. You know, we malloc some memory, we log the pointer that's allocated, we free, and then we log the dangling pointer. And when we print these two, you can see on a CHERI system, when you print a pointer, it's not just an address. We've got the address, we've got the range that it covers. At the far right, we've got the set of permissions it contains. So G is the global permission I was talking about. R and W are read and write. And then the lowercase ones are dependent permissions. So they're ones that modify some existing permissions you have. So C means if you're allowed to read and write, you're also allowed to read pointers and write pointers as well as just data. So I can give you a buffer that you can read data from, but you can't read pointers from it. G is the transitive thing that says you're allowed to load things that have the global permission, and M is the transitive mutable permission, so it permits you to load things that have write permission. And when you see this pointer printed twice, you'll see that only one of these bits has changed, which is the one labeled V over here. This is the valid bit, which is not addressable in normal operation. This is the bit that is an attestation from the hardware saying, the thing stored at this memory address is something that I have seen a valid chain of derivations from the initial pointers that covered the whole address space that I gave to the bootloader. And this is 100% deterministic. If you run this in any configuration, you'll always see that this thing is now not a usable pointer. So the baseline security that we have in this system is no pointer injection, so you can't just materialize a pointer out of an integer. If you've got some ability to inject arbitrary data from the network or whatever, you can still inject arbitrary data, you can still do data-oriented attacks, but you can't just say, hey, I know the address of this object, I'm going to materialize a pointer there. We guarantee no bounds violation, so whether you've got a pointer to a global, to a stack allocation, or to a heap allocation, the hardware will trap if you try and access out of bounds. And similarly, we've got no use after free. So how many people here do offensive work? Can I see some hands? So how many of you will have some of your favorite primitives broken by this set of guarantees? Yeah, I'm seeing a few sad people. And that is my job, to make all of you sad. So from that set of baseline security guarantees, which everything in the operating system can depend on, we want to build a compartmentalization model. And at the most fundamental level, a compartment for us is really just two things that we point to from two registers. One is some code, and one is some globals. And this is really just the stuff that's written in a C source file. It's a set of functions and a set of globals. So the program counter, which Intel calls an instruction pointer, which makes this make a lot more sense, that it's now a pointer, and so it conveys bounds and permissions and everything, refers to the code for the currently running program compartment. The global pointer is just another general purpose register that we happen to have designated for use in a special purpose. And this has read and write and global permissions. And this is the currently executing compartment's globals. And that's a little bit of an oversimplification. So in the code section, we also have read-only data so that we can use program counter relative addressing to get at all of those globals. And we also have a thing called an export table, which I'll talk through a little bit in a second. And these are all readable by the compartment, but they're not writable by the compartment. We also have one more data structure that's associated with the compartment, but which isn't accessible at all directly from the compartment. And this pair of import and export table tie together, and these is how we manage the cross-compartment transitions. So if you look in the export table for any compartment, the first entry is a copy of the program counter that you need to have in your program counter register to be executing code in that compartment. And you can use that to derive pointers that you can jump to for entry points in that compartment. It has, similarly, the global pointer for the compartment. So it has the two things that I said before, identify and describe the contents of a compartment. And beyond that, it has a load of 32-bit entries that describe an entry point. So they say, where is it within the program counter? How many argument registers are used so that the switcher that handles our compartment transition can clear the others? Does it run with interrupts enabled or interrupts disabled? And then on the other side, we have entries in the import table, which are sealed capabilities that refer to another compartment's export table. So these have the bounds of the export table, they have the address of a particular entry point entry, and they're sealed, which means that the compartment that can load them can't actually look inside them. All it can do with them is hand them to the compartment switcher, which is then able to unseal them, finds the start of the export table, load the program counter, load the global pointer, and handle that transition. The really key point there with the sealing is it guarantees integrity for those. So nothing in the system can just fabricate one of these and hand it to the compartment switcher. These have to be set up when we load the firmware image at the very first boot time. So I've sort of hand-waved a bit and talked about this in the abstract. Let's look at really what the register and memory layout look like when we're doing a compartment transition. So we've got our program counter register, and it's pointing at the currently executing compartment's code. We've got the global pointer, and it's pointing again at the currently executing compartment's globals. And we've got the stack pointer, which is the third thing that really identifies one of the roots of available memory for a part of the running system. So this refers to the current thread stack. And again, it's a CHERI pointer. It conveys bounds and permissions for the current stack. And we probably have some heap objects. So one of the nice properties of this system is that we have a shared heap that allows you to use the same really small chunk of SRAM that backs your heap between mutually distrusting compartments. And one of the things we heard about yesterday was post-quantum crypto and the need for crypto agility there, which unfortunately means doing it in software on a lot of these embedded systems. Most post-quantum crypto algorithms have really high memory requirements. But for an embedded device like this, we only need to use that memory when we're doing initial key exchange at boot when we connect to the server. So having a shared heap is really useful for that kind of thing because we start running, we do the key exchange, we allocate a load of memory, now we've got our symmetric keys, and now we can free all of those objects, and now whatever needs to run in the next phase of computation can reuse that memory. And on big systems, that's not a thing that you'd even think about talking about, because the idea that you would statically allocate memory for everything is just crazy if you're looking at a Linux or a Windows system. But in embedded systems, it's really common because you don't have a secure way of guaranteeing non-interference between mutually distrusting parts in the presence of a shared heap. Okay, so in this example, we've got some heap objects. Some are reachable from the stack, some are reachable from globals. And we want to transition to running in compartment B. So the first thing we need to think about is we kind of want compartment B to do something with some data we give it. And if you remember two things from this talk, the second thing I'd like everyone to try and remember is isolation is easy, sharing is hard. We know how to build isolated systems. You have a computer, you don't connect any wires to it, right? And now we've got fantastic security. We don't have great usability because we actually need these things to interact. And so when you want to build a system for isolation, the first thing you need to think about is, how do we do sharing? And if you can do sharing well, the isolation bit is basically free. But if you start by thinking about isolation and then try and build sharing on later, then you'll be in for a whole world of pain and suffering. So in our world, I've just added another register to this list on the left. This is the first argument register. And we put a pointer in there. And this is a pointer to one of the heap objects. And because this is a CHERI pointer, this is a thing that purely by owning it, it conveys the rights that allow you to access that object. And this is exactly the same way that you pass a pointer to some arbitrary object to any other function, not necessarily one that's a cross-domain call. So it really mirrors what the compiler already knows how to do. So when we invoke the compartment switcher, it's going to end up updating the program counter to the new compartment's code, and it'll be at a specific offset in there that's based on the entry point that you handed it from the import table. It's going to update the global pointer to the new compartment's globals. It's going to do all of these things as an atomic step, at least from the perspective of the caller. It's not actually stopping the world and doing everything in one clock cycle. The most important thing it does is subset that stack region. So when you're executing in compartment B, you've now lost access to the chunk of the stack that compartment A was using. And actually, to preserve confidentiality, it'll zero that chunk of the stack both on call and return. And again, this is something I would love to do on the 64-bit systems, but on systems where a 2 kilobyte stack is huge, it's totally feasible. On systems where a 2 megabyte stack is small, not so much. So when we finish this transition, we've lost access to all of the objects that we no longer hold pointers to. So we've lost access to the top of the stack, we've lost access to compartment A's code and globals, and we've also lost access to any of the heap objects that aren't reachable from that argument register. And if you think about this in terms of C source code, you'll never actually go through a process that looks like this. You just write a function call, and you slap an annotation on it, and you're done. So now we're in a world where we have some really strong guarantees across compartments. We've got no implicit sharing. If you want to share data from one compartment to another, you pass a pointer. So that's something that's visible in your source code. You don't need to go and look at some other policy described in a different file. You just look at the entry points for a compartment. You say, what arguments do they take? OK, those are the things that are shared. And you can clear permissions on some of those. You can do a lot before you make the call to restrict what it can do. So we can guarantee that a compartment that you call can't capture a pointer that you pass it. We can guarantee that it can't modify the object that you're pointing to. And we can provide those as either deep or shallow properties. So I can give you an immutable object that contains pointers to things that you are allowed to modify. So if I want to have my metadata at the start and then a pointer to a buffer that you're allowed to modify, that's totally fine. And we're really only just starting to explore the kinds of things that you can build with this. So in the software stack, there are really 4 trusted compartments, or I think people in this audience call these things targets. And as I said before, all of this is on GitHub. There are a few known vulnerabilities that we have solutions for. We just haven't had time to fix. Please find more. Ideally, tell us about them. Actually, ideally, give us fixes. We would welcome more contributors, but at least finding them is a great start. So when the system starts running, the hardware gives you the root pointers that grant you execute access to whole of memory, write access to the whole of memory, and seal and unseal access to the whole sealing space. So when the loader starts running, it can do absolutely anything. This is the most privileged thing in the system, and it tries really aggressively to drop privileges. The main reason I'm not too worried about the loader is it never runs on untrusted data. It runs on the firmware image that's sent to your device, which in a real deployment would be signed and would have been audited. If you are building a device that has flash memory with execute in place that can store pointers, you actually don't need the loader at all. This is entirely a link time thing. But for a lot of the potential deployments, we want to be able to dynamically load code over JTAG or from existing serial flash directly into SRAM. The last thing that the loader does is erase itself. So before it actually starts the scheduler running, before we're actually running any of the code that was in the firmware image, the loader has a little loop that goes and scrubs the stack that it was using, erases all of the code, and all of that then gets recycled for use as heap memory. So the next most privileged thing is the switcher. And this is the thing that can unseal those export table entries. It's the thing that handles exceptions when you get an interrupt, when you take a fault from going out of bounds. This is the only thing in the system that can violate our compartment isolation or thread isolation guarantees if you find a bug in it. It's about 300 instructions. So to put that in perspective, the Cell4 formally verified microkernel has about as many unverified assembly instructions in their TCB as we do. But in our case, that's all of our TCB for confidentiality and integrity. And we really would like to engage with people who can formally verify it. We have a formal model of the ISA. The control flow in this is relatively easy to reason about. A lot of it runs with interrupts disabled, so it's actually well within scope to be feasible for formal verification. And then we've got the scheduler. The scheduler is, by definition, core of your TCB for availability. The scheduler is really just a thing that is told, which thread should I run now? And it replies. And so it can obviously just say, I don't want to run any threads now, or just, I don't like that one. That thread's not going to run. When this happens, you've got an availability compromise. If the scheduler runs it in a compartment like everything else in the system. If you manage to get complete control of that compartment, you can choose which threads run, you can choose which threads don't run. But you can't see the register files, you can't see the stacks of any of the threads that run. When we take an interrupt, the switcher spills the register frame into the save area associated with the current thread, and it then seals that pointer and hands it to the scheduler. And this means the scheduler just has an opaque token for every thread that's running. When it returns from the entry point that the switcher calls, it gives back one of these things, the switcher unseals it, and the switcher then tries to use it. If it's not a valid thread entry point sealed by the switcher, that unseal operation fails, and we determine the system's under attack, and we go through a slightly convoluted path into an infinite loop. But we hit something that can be detected in hardware to trigger a reset. The final bit of our TCB is the memory allocator that I talked about. So the hardware will enforce temporal safety, it will enforce spatial safety, but it needs someone to tell it what the bounds of an allocation are. It needs someone to tell it when an object's been deallocated. So the allocator is responsible for doing that, and it's also responsible for some availability properties like enforcing quotas on different compartments. It's really important to note that the allocator is not in your TCB for anything other than heap memory. So it's not a super privileged thing. It holds a pointer to the entire heap, and it holds a pointer to the entire shadow memory. It can tamper with whatever it likes in the heap, but it has no access to anyone else's stacks. It has no access to any register save areas. It has no access to any other compartments, globals, or code. So a couple of times I mentioned auditing. When you link one of these firmware images, you build those import and export tables, and they describe everything where the loader has to set up pointers that point outside of a compartment's own code and globals region. If the loader doesn't provide you with a pointer, you can't access memory. So everything in these tables describes the entire state of any cross-compartment interaction. And this is actually the output of the linker on one of our tiny examples, fed through some Python that someone on my team wrote to generate a pretty picture. We don't expect that people would audit these by looking at the pictures, because security through obscurity is then really easy by just making the font too small. But this is just a visualization of what you can actually see. So we've got, this is, I think, example 2, if anyone wants to look in the repo, where we start with a hello world and we try and split it into 2 compartments, one that has access to the UART and one that calls that one. So we can see that the hello world compartment calls into the UART's write function. And we can see that that function will run with interrupts disabled so that we don't get interleaving of output. And then we can see all the other places it calls. And if you look at this black line here, you can see that we had a bug in this example, and we accidentally granted the UART compartment and the hello world compartment both access to the UART device. Which was kind of what this example was supposed to show you not doing. But we can audit it, and we can statically write a policy that says only the UART compartment must have access to the UART device, and you can feed the JSON output from the linker into it, and that policy engine can then say, no, sorry, security goals not met, try again. So with this system, we can give you fine-grained memory safety guarantees for existing C and C++ code bases. We can give you tools for lightweight compartmentalization, for decomposing those things into multiple mutually distrusting isolated environments. We give you safe cross-compartment sharing, And we also give you a way of building strong attestation, signing policies over the structure of this thing. So if you've got two vendors both needing to run things on the same device, we give you a way of building an audit trail for all of that. I'm going to be around for the rest of the day. Please come and ask me questions. If you're not able to find me, or you're someone watching us on the video feed and therefore not able to find me, please add questions on the CherIoT RTOS discussions page, and I'll get to them hopefully over the weekend.